Well, Kees, I have to say that it's it's an honor and a privilege to be here today in the position of Scientific Director of SRON to give this presentation. It's actually a very tough subject to predict something over an entire century, so that's going to be quite a challenge. But I wanted to say that for me, as your former student at the observatory in Utrecht, I took your courses on stellar evolution. It's an honor to stand on your shoulders, the shoulders of a giant. You put us on the map in international space research. The fact that we play a major role in international space research, astronomical space research today has a lot to do with your visionary initiatives some 50 years ago and your continued effort in the years after that to build up Dutch space research. And your work has been continued by others. Many of them are in the room today, and I feel a privilege to be part of that generation that takes over and hopefully continues in your spirit. So with that, I would like to start. If you look at the website of Kees, and here it is, you have your own homepage. You actually see that Kees is actually still very much an active researcher, and you can actually subscribe to his website. I actually recommend that to do that. The number of registered persons is 71, so I think we certainly can expect to see this number increase significantly after today. You put things like your talks on your website. You keep it up to date, because even the talk of today that we will hear half an hour from now after I finish is already included in your website, and we know that Monday the 4th of July you will be found in Den Burg to talk about our fascinating universe, and here's a list of the talks you gave already earlier this year. It's quite an impressive list, certainly much longer than my list of talks that I gave this year. You are a surprising scientist, and sometimes I think if we would all go outside and actually check the observations, I'm not sure that we would all agree with this quote. I think that there must be a journalist in between what you actually said and what was written down in the press, because that's the only way I can understand this particular statement of yours. So I thought, with these things, I should actually start a topic of my talk, which is also, you know, it's very hard. I struggled this week trying to put this together. What you see here is the launch of the Space Shuttle Endeavour of this week, May 16th, its last journey, and I think this is one of the examples of why it is so hard to predict the future. You know, when the space research program was started some 30 years ago, it was expected that this would be the main way where we would launch satellites into space, and that we would have a shuttle launch every week, and it would be like, you know, we're taking some standard thing into space. And we know that this has not come through. That the space research program has had its successes, but it didn't grow into what people thought it would grow into some 30 years ago. So it's very hard to predict the future. Of course, astronomers are extremely grateful to the Space Shuttle program, because the Hubble Space Telescope, which I think is really the most successful telescope maybe since the 1600s, when the first telescope was used to study the moons of Jupiter. I think we are all very grateful for the Space Shuttle to be able to take the Hubble Space Telescope into this bay and fix it 4 times, and now it has put it out again a few years ago at its last repair mission. So I think the Space Shuttle has had an enormous impact on astronomical space research by putting in this fantastic machinery. So if you talk about the future of astronomical space research, so this afternoon I really want to focus on astronomical space research. You know that from our institute and other institutes in the Netherlands, we also participate in other aspects of space research, in particular the Earth-oriented science, but for this afternoon I'll stick to astronomical space research. The thing is that new telescopes, they provide breakthroughs in science. That's what they're built for and designed for to do, but usually in areas where they didn't expect to have these breakthroughs in when you design the instrument. And so that's one of the challenges and one of the fascinating, the nice things about science. It's so very unpredictable. So predicting the future of space research in the 21st century is an impossible task. But okay, let's see how far we go. And even, you know, on a time scale of 10 or 20 years, I think it's very hard to do this. And then I think this quote by Isaac Asimov has sort of kept me going for the past few days when I tried to prepare for this talk. As those people who think they know everything are a great annoyance to those of us who actually know everything. So I certainly don't claim to be a member of either group. So that is the disclaimer of this talk. Let's start at the beginning and ask ourselves the scientific questions that are currently sort of at the top of the list of most astronomers that do astronomical research. I listed the 4 bullets that you can find on European Astronaut and also on the Cosmic Vision Plan of ESA. And you're all familiar with them, so I can go through them very quickly. Do we understand the extremes of the universe? How do galaxies form and how do they evolve? How do stars and planets form and how do we fit in? So what's the origin of life? And a very similar series of questions, slightly differently formulated, you can find in ESA's Cosmic Vision Plan for 2015-2025. So both for ground-based and space-based astronomy, these are these are 4 very important questions. I think you could also focus on maybe 2 of them. I'll do so in the remainder of my talk a bit. The 2 origin questions. So the origin of the universe and the origin of the solar system and life as we know it. This is really the fantastic suite of instrumentation that astronomers have at their disposal. Some of them maybe a bit later than we thought, but still ground-based and space-based all together. And this is really what modern astrophysics is all about. We have a multi-frequency approach, so we try to answer questions, astrophysical questions, and we use whatever photons we can get at any wavelength or any messenger, gravitational waves or particles that come to us from outer space in order to answer our scientific questions. And I think the fact that we have such a success in astrophysics in the past, let's say 30 years or so, is mainly due to the fact that technological progress has been so fast that instruments have become more sophisticated and more complex, and we could actually access the entire electromagnetic spectrum and even more hopefully in the future in order to answer these scientific questions. You can see that sort of this is the state of the art in sort of where we are now, 2010 to 2015, worldwide, ground-based and space-based. I'm not going to go through all these missions, but you can see, you know, it's pretty nicely filled throughout this entire wavelength range, both from the ground and from space. And then if you go to beyond 2018, I think the Hubble Space Telescope, the James Webb Space Telescope is here, should be here and not in the previous slides, so it's moved from one slide to the other. You can see actually that, well, it's not as full. The previous picture was nice and full with instrumentation that we know that's going to be there because it's already being built and so has been decided that we go ahead and do it. But if you go beyond 2018, things become a lot less obvious, and this is of course slightly worrying because we really need to plan 10 or 15 years ahead in order to fill those gaps in order to answer the scientific question that we'd like to know. Okay, zooming into the Dutch situation and taking sort of on where Harm left off. So where is our Dutch involvement in space research projects? So really, well, I'm forgetting about the ground-based astronomy for the moment. Of course, the scientific questions that are asked for ground-based and space-based facilities equally. We are very fortunate. There are 3 major missions that we are involved in from the Dutch side with SRON involvement that are currently still producing fantastic data. That's Newton X-ray telescope launched by ESA some 10 years ago, Chandra X-ray telescope launched by NASA some 10 or 11 years ago, and then the Herschel satellite with the HiFi instrument, the most complex space instrument that the Netherlands has developed under guidance of SRON, is still actively hunting for molecules in space. So fantastic that the astronomical community in the Netherlands and worldwide is actually being able to harvest from these developments. And then if you look into the nearest future, there are approved missions. We are fortunate to be part of the Astro-H project in Japan, approved by JAXA, that will be launched in 2014, which will carry an X-ray spectrometer, where SRON is contributing. And then there are two projects, Gaia, where NOVA has a modest but interesting contribution, and Gaia will map map the stars in our galaxy, so, and get their velocities, and so we will know exactly what the potential of the galaxy is and know distances to the stars, and that will revolutionize our understanding of stars and the nature of our galaxy. And then in 2018 the James Webb Space Telescope will be launched with a mid-infrared spectrograph on board, which was designed in part by NOVA in a large international consortium with some and that will fly hopefully in 2018. I'll get back to the James Webb in the second part of my talk. You look to the cosmic vision plan of ESA for the coming 10 years, so up to or a bit more 10 years, 15 years, up to 2025. Then there's a lot of discussion, and this year is going to be an important one because ESA will down select a lot of these and will decide on building actually a few of those. ESA has a program in which it defines smaller missions, or say medium-sized missions of a few hundred million euros, and larger missions that are in the order of a European contribution of 600 or 700 million euros. And so for the medium-sized missions, these are still in the running, and the bold ones are the ones where there's a strong Dutch interest in contributing. And for the large missions, there's actually IXO, which has recently been renamed to Athena, so you can see that things are moving in the ESA program. And also here is a planetary mission, which has also been renamed lately. And if you compare that to the European, to the US program, the outcome of the decadal survey of NASA, actually not of NASA, but of the US astronomical community, then actually they have selected one of their top priorities, W first, which is going to be similar to Euclid. I'll come back to these in a moment. For SRON, Spica is going to be a very interesting mission. Has not been selected, so we're still in the study phase. It's a mission of opportunity for the ESA program, and the main institute that is pushing this is JAXA, so it's a Japanese initiative. It's let's say it's the dream of infrared astronomy beyond ISO and beyond Herschel, because it's really a cooled Herschel, and this is really what you want, and it's the next enormously big step after James Webb in the far infrared wavelength range. James Webb is slightly shorter wavelength range, so this is a absolutely fantastic machinery, a big international research infrastructure, and there will be a European contribution if approved by Japan. So Japan is in the process of thinking about approving it. If approved, then Europe will build an instrument called Safari, and SRON is fortunate to be the principal investigator institute for this European consortium that will build this instrument. Safari will be the biggest instrument on board of Spica, so it will be a very prominent European presence and in this international research facility. And here are a few of the science cases outlined that Spica will address. Two of the origins questions, really: the origin of the universe, how did it evolve, and the origin of solar systems and complex chemistry in these solar systems. If I zoom into that origin question a bit more, so origin of the solar system and life, there are all these missions that are either approved or under study that address various aspects of this particular question, either trying to understand the formation of stars and planetary systems, or trying to understand the nature of exoplanets around stars. And that is, I think, a very promising and strongly developing research. And so we're talking about future, so we can let our imagination run loose, and I'll go more loose as this talk evolves, so fasten your seatbelts. So imagine that you could image the water in the inner disk, in the inner regions of a planet-forming disk. So that, I think, if you ask the people who study the chemistry in these types of objects, then this is something they really love to do. You can't do this from the ground, because obviously water you can't detect from the ground, because the Earth's atmosphere is in the way, and so you need to go to space, and you can't do this. You can't do this with Spica, because Spica doesn't have the spatial resolution to do this. You need to do something more clever, and if you're looking for water, you might just as well also look for the complex organic molecules in these inner parts of these forming systems. So this is everything in terms of building blocks of life before a planet is actually formed. Exoplanets. A revolution in the past 15 years, and even more so perhaps in the past 7 or 8 years, when the first spectra of exoplanets were being detected with, for instance, the Spitzer Space Telescope wasn't built to do this, but it did it anyhow. And what you see here is the trick where people use the fact that sometimes you see the planet go behind the star, and sometimes it's in front of the star, and you subtract the two signals, and then you get spectra of exoplanets like this one. And we actually can see molecules like carbon dioxide, water, and methane in the atmospheres of these exoplanets. The fact that I can give this talk and show you this picture is a complete revolution, and you couldn't have imagined this a few years ago. And that's why it's so hard to predict the future of this field over the next even 5 or 10 years. We can expect surprises. This is the dream. The dream is to detect the spectrum. Here's a wavelength, here's a flux of an Earth-like exoplanet in the habitable zone around a solar-type star in the solar neighborhood, and then to look at the fingerprint of its atmosphere. You can see here the spectrum of 3 planets in our inner solar system: Venus, Earth, and Mars. And the Earth spectrum, it looks very different from that of lifeless Mars and Venus. And you can see that the ozone and water is very prominent. So one of the holy grails is to try to get this spectrum of an Earth-like planet, really of an exo-Earth, and to actually find ozone. Ozone is the fingerprint of an atmosphere which is out of chemical equilibrium, where you need biological activity in order to sustain it. So looking for ozone. What do you need? I've given you a few examples. Water in the inner protoplanetary disk to study, or organics to study the building blocks of life in the inner solar systems of forming planetary systems. Studying the exoplanets around solar-type stars. What you need are space interferometers. So you use not one telescope, but you use a fleet of telescopes. You couple them together, and you use the collecting area and the size, the separation between those, like we do with LOFAR or with Westerbork, in order to improve spatial resolution. You can see for ground-based and some space-based telescopes, spatial resolution at the very long wavelengths is very good. At the shorter wavelengths is very good, but here in this wavelength range is pretty lousy, so we need to build on that. Then the other origins question, origin and evolution of the universe. I think there's a whole suite of telescopes, ground-based, space-based. I'm focusing here on the space-based ones, like James Webb, like Spica, like IXO, that address several aspects of what you would like to understand about the origin and evolution of our universe and the galaxies that are in it. Here are satellites. Some of them are active. We heard a talk this morning about Planck. Some of them are being proposed. Some of them are approved but delayed. That will answer in various ways the same question: how did our universe originate and how did it evolve? The Hubble Deep Field and hunting for the most distant galaxy. We have the record holder, I think. I actually forgot, because the record keeps shifting. Z equals 8, I think, was the 10. Record. 10, sorry, 10, thank you. So that's an amazing situation. Somewhere in here there must be a galaxy that is among the first generation of galaxies. And just as an example, James Webb Space Telescope but all other facilities as well are being designed and built now to search for those primordial galaxies and study their properties. You can go to X-rays, and of course there's a long tradition in the space research in the Netherlands, trying to map the hot gas in the universe to try to detect the first clusters of galaxies. And here's a simulation of what such an observation might look like with a telescope that used to be in the ESA program called IXO, the International X-ray Observatory. That was a global collaboration between the US, Europe and Japan. That sort of is no longer the case because of problems on the US side of funding. I'll come back to that in a moment. And now Europe is trying to see where we can go with the Europe-only version of this. And this is something I think we should try to get at every wavelength. Here's a sort of a technical slide where this is a design for one of the instruments on board of what IXO was supposed to deliver. An X-ray, so a two-dimensional camera of which every pixel is also frequency dependent. So you can take an integral field spectrum, but you don't need the optics. So every pixel itself, just by its design, is wavelength sensitive and at a spectral resolution which is really wonderful. And I think if we could get that for every wavelength, that type of detectors, I think that would be an incredible breakthrough. You can study large-scale structures with those detectors, like finding out the nature of the cosmic web and the chemical evolution of the universe. Very interesting, very interesting questions. Well, this is about a whole century, right? So we can really lose our reality for a moment, and let's really dream about things you would, completely detached from any reality about what we can do technically now, but just say, okay, what would you like to do? And I've asked several people in the audience here in the course of the Dutch Astronomers Conference, and so this is sort of a summary of my own preference and some of the things that people said that they would like to have, so detached from any technological reality, but nevertheless, well, so imagine that we could image the surface of a neutron star. That would be nice. Michiel, I think we don't need timing anymore, because you can actually observe how a blob of gas actually rotates around such a accreting neutron star and falls onto its surface. So you can study all kinds of general relativistic effects by just observing a gas near the event horizon of a black hole. I think if you imagine that type of science, well, what do you need? You need an X-ray interferometer, and there are even thoughts about how to do that, raising incidence mirrors that actually focus it, and then you get a standard two-element interferometer. If you read the description of this, that actually says it has some technical challenges to it. But hey, it's a whole century we're talking about, right? So this is the kind of spatial resolution that these types of things would like to have. Then, I think it was almost 20 years ago that I was at a conference in Spain where a NASA official said, and was very serious about it, we at NASA want to map the surfaces and the distribution of continents on exoplanets. And I thought, okay, we talk about the whole century, so let's throw this one in as well. So here is a picture of the early Earth. This is Mars. So let's try to imagine to actually take images of the surface of an exo-Earth. So rather not detect just the integrated light of it, but spatially resolve it and discover where the continents are, where the oceans are, and even, if you take then a picture at different times, you can actually see where the civilizations are, because, sometimes the light is on and sometimes the light is off. We heard wonderful talks today about stellar populations in nearby galaxies and the tremendous diagnostic value of such spectra and photometry of individual stars, where you can spatially resolve these populations of stars. This is Omega Centauri. It's a pity that Kuhn is not here because this is one of his favorite acronyms. So imagine that you could spatially resolve the stellar population not in the local universe, but let's say at z equals 6 or z equals 8, where you would be able to pick out a star and take its spectrum and know it was one of the first stars in the universe. So that is a type of science that one really would like to do in hopefully the coming century. So, what are we talking about? Well, it's big science, these are big questions, and we need big facilities. And this is where things become rather awkward. James Webb, that's exceeding $5 billion cost as we, and counting, I should say. And to put this into perspective, you know, it's not quite, but it's getting there. It's similar to launching CERN into an orbit, right? CERN, the accelerator in Geneva, is of the order of this amount. So you can imagine that NASA is chewing away on this, and this has serious implications for the US astrophysics space program. So this is not good news. The fact that it's so expensive is really hurting global astrophysics, I think. As a consequence, IXO, which was a beautiful international collaboration between NASA, ESA, and JAXA, well, sort of fell through, and now in Europe there's a Europe-only Endoscope study being done in order to see what can you do if you would do it from Europe only, and what type of science we could actually do and keep, and what things should we not try with such a descoped telescope. Darwin, that was the dream that ESA had some years ago to actually put a space interferometer and measure by nulling interferometry the spectrum of such an Earth exoplanet and try to find the ozone. That sort of died in the last cosmic vision selection, and we really have no idea when this will happen again, but the dream is still there. LISA, same story. LISA was a collaboration between the US and Europe measuring gravitational waves. Again, the US has not given that high priority because of also budget problems, and so now there's a Europe-only study underway. So how to deal with this? So what do we do beyond Planck, James Webb, Spica, and suppose that we got the IXO? What do we do beyond IXO? That's a tough question. I don't claim that I have the ready-made answer, but I think, you know, we could think about smarter satellites, things that are light-weighted, things that are smaller. And here's an example of a satellite which is a small thing. I actually forgot to look up at the dimensions, but I think it's really sort of a leaf of bread type of satellite, which will look for the signal of exoplanets by staring at stars and measuring the transits of planets in front of the stars. And this is a project where people from MIT are involved. I think this is certainly a niche science where you can actually do very interesting things from space with relatively modest instrumentation. But maybe more importantly is that, you know, technology is really has always driven astrophysics to the next level of discovery space. And I think just taking as an example the problem of detecting an exoplanet around a bright star, you need to get rid of the light of the star in order to see the faint exoplanet. And this is a coronagraph design by a group in the US. And if you put a telescope at a very large distance and put this thing in the beam, so you have two free-floating things in space and one in front of your telescope obscuring the star, this can block the light of the star extremely efficiently, and then you can look at very faint signals of planets around these stars without maybe having to use the interferometer. So this is just an example of let's say, the technological inventivity of people in order to still take the next step in astrophysics. So here are a few of the things you could think of. Light weighting, so every kilo costs I don't know how many million, so if you can do it lighter, it's always a good idea. I think the interferometry is going to be a very important thing for the future, and hopefully with many elements. So if one fails, you still have 25 left. I thought I was jealous of the talk that we heard of the study of the streamings of the Earth's ocean, where you have several thousand detectors that float around in the oceans, and that you can measure the flows on Earth with these of water on Earth with these things. I had the picture of having these thousands of small satellites all talking together and measuring things for us in space. So that was doing something. Extremely high spectral resolution. Hi-Fi on board of Herschel is actually providing spatial resolution because it has such high spectral resolution. Of course, you need a model, but you know, if you're clever about it, you can actually disentangle many of the spatial components by just taking very high spectral resolution. So maybe, you know, taking high spectral resolution is a poor man's solution to high spatial resolution, at least for some areas. That certainly very looks like that. We could try to do that. If your collecting area is hard to increase, so for instance you can't build a 100-meter class telescope in space, so what do you do then? Well, maybe you improve your sensor technology. Oh, I forgot one actually here. To eliminate these dispersive optics and so get integral field spectroscopy like we do now with these X-ray cameras, but do that also for other wavelengths. I think that would be wonderful. And then as several people have pointed out to me, and I think Peter Jonker has been one of them already earlier, is that the time domain is a domain where that's the next frontier also in discovery space. So time variability offers a wonderful way to explore new physics. We saw the Lofa transient talk this morning by Ralph. We heard the time variability of pulsating stars, and so the time domain is, I think, very interesting. And then I think polarimetry, although it's a difficult technique, will certainly will give us very interesting new ways of looking at several of the important scientific questions, especially if you use it in the context of other diagnostics. So, I think what we need to do is continue to invest in fundamental research and technology. Institutes like SRON are built, and we would like to do that, not by ourselves, but with universities, with other institutes, knowledge institutes, and with industry in the Netherlands and abroad. But we need enthusiastic people. Well, SRON has a whole lab of enthusiastic people, and they work with a whole country of enthusiastic astronomers. And this is what I think is our big selling point. As Harm was pointing out, the astronomers always wanted to use our photons, the SRON photons, and vice versa. We want to know your ideas for the next type of instruments that we should build. So I think, you know, here are a few quotes. Thinking the unconventional is important. So out-of-the-box thinking, very interesting. Try to continue to do that. And just the excitement, you know, being part of space research. This is not, you know, not everybody is able to do that. This is really, you know, a great opportunity to make a dream come true. So, I'll stop here with, I think, a picture I really like a lot, which is the Earth as viewed from Voyager 1, as Voyager 1 was just about to exit the solar system. So it puts you into some kind of perspective of this little blue dot that we all live on, and we look outside to this interesting universe that we try to understand. I think it was a great idea by Carl Sagan to take the Voyager 1 camera and point it back, because I think this really is maybe one of the most impressive pictures ever taken from space. So I stop here. Thank you very much.